Alright, let's start the new unit. We're going to be talking about center of mass. We'll abbreviate that COM. And then we're going to get into linear momentum. And I'm going to talk a little bit about rotations also, which is the next step. What happens if we... Right now, we're treating everything like a particle. Particles don't rotate. They may, but ours do not. We just treat it like a particle, and they have some trajectory or even some mass. We treat it as a particle, right? Well, we need to learn about the center of mass of an object. That's literally, if you were to have a bunch of particles, they could all have different masses, and you wanted to know where's like the average mass, or where's, if I represented all of these as one point, where would it be? Well, we can calculate that mathematically, and it's probably going to be somewhere around there. That's just my guess, just because these ones are pretty heavy, so maybe a little bit higher. We can calculate that mathematically, and why do we need to do this? Because the center of mass allows us to treat things that are not a particle as a particle. So we could have a bunch of different masses, but still solve the problem as if we just had one big mass, capital M. But when we do this, we have to account for two things: that all of the mass is concentrated there, concentrated at M, capital M, and for this set of problems, we have to say that all the forces are concurrent through here. All the external forces are going to go through M. And this is important because if, let's say, I had some distribution of mass, and this is some actual volume, right? But still, it's a little system of particles. We can sum all the particles up, or we can integrate it. I'll show you how. It doesn't really matter. But in this case, pretend it's all one material. Maybe stainless steel. It's just cut into a weird shape. And the center of mass is somewhere around here. If I were to apply a force like this, that's going to give me some acceleration, right? In the same exact direction. Or if this is the summation of my forces, right? I could have a bunch of forces acting on it. But if I were to apply that same force some distance d away, and this is the most simple perpendicular case, so it's a 90-degree angle, that's going to cause a rotation. It'll cause an acceleration also, not quite as much, but it's going to cause a rotation. This is what we call torque. This is where we're leading to at the end of this unit. I just want to introduce it now, and torque would be equal to that force times that perpendicular distance d. So that has to be perpendicular. I'll teach you the details of if it is or isn't, and how it affects the torque, and that causes some rotation. Okay, so right now center of mass, and the goal is basically if we have two particles, n number of particles, or a system of particles, or some sort of volume, we can ignore the fact that it is a bunch of particles and just treat it like one particle. Well, how do we do that? Well, first let's imagine if we just have two particles. Oop, that didn't work. If we have two particles, we'll say we have some M1 here and some mass 2 here. Now M1 is not equal to M2 in this case. If they were equal, then we could use symmetry. I'm going to say that word a few times. Symmetry will get you far. Symmetry would tell us that whatever this distance d is between the two, well, the center of mass would be at 1/2 of that distance, right? Well, let's pretend they're not the same mass. Let's say maybe mass 2 is bigger, so that's going to actually push it over from the center point and put it somewhere here. Let's use a different color. Let's say the center of mass is right there. Center of mass. We can describe its position. Call it XCOM. From the y-axis. Just like we can describe the position of mass 1 and mass 2. What we get is we need one more coordinate. We need the distance between the two. So the distance between mass 1 and mass 2. Alright, if we have that information, then we can find the center of mass and then treat these two particles that may be moving off together at some same velocity. We can just treat them as one particle moving off with one velocity with a combined mass, right? So remember, M1 plus M2 would be capital M in this case, and we can have a bunch of M's. We can have a bunch of masses. Okay, so using this right here, we can describe the x-coordinate for the center of mass as M1 x1 plus M2 times x2, all divided by the combined mass. Okay. We can extend this further to n number of particles. Right, so n could equal anything. Obviously a positive quantity. We don't have negative quantities of particles. Or maybe in particle physics, I don't know. There's still a lot of questions out there unanswered. But say we have n number of particles. We could have 20, we could have 529. We can still find that center of mass for the x-coordinate by saying m1 x1 plus m2 x2 plus m3 x3 plus dot 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 plus m n x n. So, where n is the nth particle. And then we have to divide that all by the combined mass. So this is all of those masses added up. It's a lot easier to write this as a summation. We can say this mass is constant, we can pull it out, and then say it's multiplied by the summation from I is equal to 1 to n of m sub I x sub I. And guess what? We can extend it into 3 dimensions. We can say the y-coordinate center of mass is 1 over the mass times the summation from 1 to n. And then we'd be looking at the y coordinate. And the same thing for a z coordinate. Alright, just think about something real quick. Why do we need to know the center of mass? And think about this. If you had two masses attached to a spring, and they could be oscillating back and forth, if you threw this thing through the air, if we had to, it'd be a lot easier if we could just treat this as one particle, right? Well, guess what? You can. The center of mass actually never changes when two masses oscillate on a spring, so we could treat this just as one particle going on. It makes our life easier. How about that? So if you wanted to make this easier right here, take all of these and we can describe the center of mass with a vector, right? We can describe if there's a system of particles, a blob of particles right here. We could describe the center of mass with some vector pointing to it, and we would call it the x coordinate in the I direction, the y coordinate for the center of mass in the j direction, and the z coordinate for the center of mass in the k direction. You can reduce that even further if you just wanted to, I guess, memorize or write down one definition or something. Oh yeah, this is all divided by our mass. Sorry. Wait, no. Take that back. That's just a vector. There's no mass in a vector. That's a position vector. But if I wanted to write this as a summation, I guess this is just, like I said, the best way to put it on your note card. We would pull the combined mass out, and we'd say from 1 to n, we'd look at the mass times the position vector. I think this one's honestly makes a little more sense, but this is mathematics for you right there. As long as you can describe the center of mass of a distribution of particles with a vector, you're good. I will never ask you to do this. Okay, well, what if we had some sort of solid body? What if we have maybe a cone and it's all made up of the same stuff? Well, where would the center of mass be? We can use symmetry to figure out the x and y coordinate, or depends what we're calling. We can figure out this coordinate, right? But we would need to do a little math to figure out where the center of mass lies along this line right here. But common sense is going to tell us it's not going to be at the halfway point, right? There's a lot less mass here than there is down here. So let's just go ahead and represent it like this for now. Somewhere closer to the base, because the base is heavy. Oh yeah, I'm actually remaking this video, and I forgot this the first time. The Leaning Tower of Pisa. Why doesn't it fall over? And when will it fall over? I should have drawn the tower first. I'm making this pretty drastic. Yeah, that'll work for now. There's our leaning tower of Pisa. Why doesn't it fall over? Well, the center of mass is somewhere about here, and it's actually, if you draw a line straight down, the center of mass falls inside the base. This is the base right here. As soon as that leaning tower of Pisa falls far enough over to where the center of mass falls outside the base, and if you're in engineering 101, I probably taught you this, it's going to start falling over. So as soon as the center of mass is outside the base, and it might go a little bit further outside the base, right? There's a foundation and stuff, and they're actually, I believe, reinforcing it in different ways, but that's the center of mass for you. I'm just trying to give you some examples. But let's get back to solid bodies. If we had a solid body like this, how could we find that point right there? First, we have to realize that we can only do this for uniform mass distributions. Meaning there's a bunch of unknown air pockets inside here, we don't know where the air pockets are or something, or there's pieces are scattered around in a manner that we don't know, we can't use this. This has to be for uniform mass distributions, meaning it's all made of the same material, right? It's all solid stainless steel, and it's no more dense in one point than it is in any other point. Well, we can still find the center of mass, but we just turn those summations that we had above into integrals. So it's still 1 over m, and the summation turns into the integral of x dm. You're integrating with respect to the mass. The y is similarly the integral of y dm, and for z, guess what? It's z dm. Okay, we introduced volume, and I know you've talked about volume before, but we introduced volume at the beginning when we were talking about units. And it's the mass the density. Right? We introduced what density was by talking about other types of units combined, which give us derived units. Density was one of those derived units, and it was the mass per unit volume. We can look at this at the differential level too and say the differential mass per differential unit volume. And what that gives us when we rearrange is that dm is equal to the mass over the volume dV. Now, what does that do? That turns these formulas right here into 1 over v times the integral of x dV. And the same for y and z. Alright, there's a little section in the book, really symmetry is your friend here. Symmetry and just common knowledge that you've gained through your life, I guess common sense, right? If we have a cube and it's all made of the same material, ding, 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 ding. Where's the center of mass? If it's all made of the center of the same material, then I bet you it is halfway between here and here, so somewhere along this line. I bet you it's halfway between here and here, so somewhere along this line. And I bet you it's halfway between here and here, so somewhere along this line. And when you project those, you find your center of mass. So symmetry is your friend. Same thing with a sphere. Right? You have a sphere. The center of mass is going to be right at the center. And there's you can look up what the center of mass is for many objects. I believe there's a table in this book. If not, the internet's your friend there. But try to use symmetry as much as possible. If two masses are equal to each other, symmetry is your friend, because you know that the center of mass is going to be exactly halfway between there. If this is some distance d, then d over 2 and d over 2 is where you will find the center of mass. Try to use symmetry as much as possible. And I'm going to assign you a problem that I think will help reinforce that, and it will be a quiz point, so please do that one. Alright.